All right, the LOL diagrams are back, ladies and gentlemen. I know how much you missed these in the past few days. So this is a great way to model thermal energy being passed back and forth, just like we saw in those previous slides. So let's consider this example problem. Let's say that a cup of hot coffee cools as it sits on a countertop. So just like the LOL diagrams or the energy bar charts last time, we have our initial, our final, we have made our L's with our charts, and we have a circle in which we're going to write our system. Um, so typically these systems that we're going to be analyzing is just going to be one substance. I think it makes sense to look at the cup of hot coffee. So the first step is always to identify the system. We have to figure out what we are analyzing before we can actually analyze it. Then we're going to figure out the initial and the final energy states. You'll notice here that there are two types of energy written, ETH and EPH. This one we already know, that's the thermal energy, right? EPH we have not discussed. We will talk about that in a little bit, so let's just ignore that one for now. Right now you should be focusing on the thermal energy, which you know is the total energy due to the motion of the particles. So this is a cup of hot coffee. So think about it. Is it going to have high amounts of thermal energy or low amounts of thermal energy, relatively speaking? I'm probably going to model it with pretty high amounts of thermal energy. Coffee, in order to make good coffee, you have to bring the water pretty close to boiling point, about 200 degrees Fahrenheit, which is, I don't know, 97 degrees Celsius or something like that. So it's going to be quite hot. So I'm going to say that any object that is quite hot is going to have 4 bars, 1, 2, 3, 4 bars of thermal energy. You could do this with 3 bars representing a hot object. It really does not matter. I'm going to say 4 bars equals a hot object. It's cooling down to room temperature. Eventually it's going to reach the same temperature as the room. How do I know that? Well, what is causing the coffee to cool down? It's transferring some of its kinetic energy away to a lower temperature object, isn't it? We could actually analyze this in a very complicated way. I'm going to try and make it simpler. So here's the cup of coffee sitting on the countertop. So here's the cup of coffee sitting on the countertop, and it's pretty hot. So the particles in the coffee are moving quite rapidly. So I need to draw some large arrows here, random motion. Um, and it's hard to draw this, but we could draw out the particles of the cup, the particles of the counter, the particles of the air. We could draw all those particles and how they're moving. All of those substances are probably going to be moving a little bit more slowly, but which one do you think has the biggest impact? Probably the air, because the air, there's more of it around the coffee cup, all around the coffee cup. So you'll notice that I'm drawing the particles of the air, these gas particles, moving more slowly. So what's going to happen? Well, the air particles are going to come and collide with the surface of the coffee. There's going to be a collision. What's going to happen during this collision? Well, the higher energy coffee particles are going to give some of that kinetic energy away to the lower energy air particles. The air particle is going to bounce off the little bit higher kinetic energy, and the coffee particle is going to bounce off a little bit lower kinetic energy. So that's why the coffee cools, very simply because thermal energy is flowing out of the cup of coffee into the air due to the collisions of particles. The hot, rapidly moving coffee particles are colliding with the air particles, giving some of their energy to the air particles. So quite literally, the air will warm up. It'll get a little bit hotter, but there's so much of it that we don't really feel that happening. So the coffee is going to end up being room temperature. This is going to come to thermal equilibrium, and because there's so much room air compared to the coffee is pretty much going to obtain the temperature of the air. So I'm going to represent room temperature with 2 bars, just like this. So am I done? No, if I finished here, then I would be implying to you that energy has just been destroyed. I went from 4 bars of thermal energy to 2 bars of thermal energy. and we're not going to destroy energy. We can't break the laws of the universe. I can't. I don't know about you. That'd be pretty cool. So I need to show what? I need to show that some of this energy is flowing out. 2 bars of energy flowing out into the room air. I like to sometimes show where the energy is flowing out into. So I'm going to write room air right here. The energy is flowing from the coffee into the room air. And it is flowing as thermal energy. It has not been transformed into any other type. So energy is being transferred out of the coffee into the room air because the coffee particles are moving more rapidly and they're transferring their energy due to collisions that are taking place. Okay, let's see if we can do another practice problem. This one is going to be, I think, pretty simple for you. I want you to try it. A can of cold soda warms as it sits out on the counter. So I would like for you to try this, and I'll be back in a second, and you can see my answer. And again, let's ignore that phase energy. Don't forget to define your system first. Okay, so here you can see my very correct answer. No, this is not correct. Mr. Thurman, what are you thinking? Thermal energy is not going to flow out of the can of soda. How do I know that? Well, first of all, the question tells me it's warming up, so I know that its thermal energy content must be increasing. Its particles must be moving more rapidly if it's going to warm up. So this is not correct. It's not going to go from 1 bar of thermal energy to 0 bars of thermal energy flowing out of it. Second of all, remember what direction heat flow always occurs in. It always occurs from hot objects or from high temperature objects to cold objects or low temp objects. So this is completely backwards. The air surrounding the soda is at room temperature. It's warmer. So energy is going to flow from the air, the room air, into the cold soda. So I need to try this again. Okay, so here's my correct answer. I start with cold soda, so it has very low thermal energy content. I'm going to say about 1 bar is going to be something that's cold. I know it's going to warm up and become the temperature of the air, room temperature. That's going to be 2 bars of thermal energy, just like last time. So the room air then has got to be transferring 1 bar of thermal energy into that can of soda. Technically speaking, the room is going to get a tiny, 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 tiny bit colder. Why does the soda warm up so much, but the air does not cool down very much? The soda gained the exact same amount of thermal energy that the air lost, right? The room air lost 1 box of thermal energy. The soda had to gain that box of thermal energy. So why does the room air not feel cold now? Well, because remember, thermal energy depends on how much stuff there is, and there's a lot of air particles compared to soda particles. So yes, technically speaking, if we had some sort of super high-tech temperature measurement tool, we would see that the air temperature gets a little bit smaller. The air temperature goes down as energy flows from the air into the can of soda, once again due to the collisions of particles, the transfer of kinetic energy. But because there's so much room air, so many air particles, it doesn't happen a lot. The temperature of the air does not change to any significant extent. But that's not even part of the question. The question was, I needed to model graphically using an LOL chart, energy bar chart, how a can of cold soda warms up when it sits out on a counter. The room air, sometimes we just refer to this as the surroundings, because technically speaking, the table, the countertop, and the cup are all transferring energy as well. So sometimes we'll just refer to this as the surroundings, the system, and then the surroundings. The surroundings have transferred energy in. Energy flows from high temp to low temp due to collisions of moving particles. Let's do a last example. A piece of ice melts as it sits out on a countertop. So think about this. The particles of the ice are moving very, very, very slowly, so I have hardly any motion. Are they moving at all? Yeah, they're going to be moving at all. Even solids, even objects that are solids have their particles have motion. It's just mainly vibrations at this point. Those particles are locked into place, kind of vibrating. So that's my beginning state. My ending state is going to be just a liquidy mess here, where the water particles now are moving more rapidly. So you know, obviously, that in order to melt, ice has to warm up. And now my water here is moving more rapidly. So pretty simple. Let's say that the water, H2O, solid, liquid, it's all H2O, it's all water, um, is my system. It's going to start out really, really cold. So you could do 1 bar, you could do half a bar of thermal energy to show how cold it is. It's frozen solid. It's 0 degrees Celsius or below. I'm going to keep it simple just with 1 bar of thermal energy. How much thermal energy is it going to end with? Well, probably 2 because it's going to warm up to room temperature. So I need to show, just like last time, 1 bar of thermal energy flowing in from the surroundings. I'm going to abbreviate that. Thermal energy from the surroundings into the system. Yay, now I have a warmer sample. My water has warmed up. But is this enough to model fully the changes that have taken place? No, because what else has happened besides the water temperature increasing? We've also had a change in phase. The water has gone from solid water, water as a solid, to water as a liquid. That's what it means to melt, right? So I need to take that into consideration and adjust my bar chart. I have now got to consider this thing that we are calling phase energy. So the answer that I have right now is not the whole picture. It is not fully correct. Something else is happening, and it has to do with how the particles are arranged when they are in these phases. So we need to talk about that.